Greetings, this is Mr. Garwood with our continuing video series on Calculus, second edition by Briggs, Cochran, and Gillette. This video is going to start our discussion of related rates. I have a bad feeling that I'm going to have to make a whole lot of videos because there's a lot of different ways to do this. And really, it depends on every problem. And related rates is our really first big chance in calculus to really do some word problems and talk about some real-world phenomena and use calculus to give us a meaningful answer. I am looking at example 1, which is on page 179 of your textbook. And I'm going to bring it over here, and you can pause your screen, and let me zoom in a little bit so you can see it. And the question goes, an oil rig springs a leak in calm seas, and the oil spreads in a circular patch around the ring.
I don't understand.
And my phone is being terrible. And so if the radius of the oil patch increases at a rate of 30 meters per hour, how fast is the area of the patch increasing when the patch has a radius of 100 meters? Wow, so if you have not done so already, if you want to write this down or if you want to make sure you understand it, there's the problem. There's even a picture here of, we got a well on our, an oil well that's leaking, hashtag, what was it, the thing, the BP oil spill, or something Horizon in the Gulf of Mexico. Now, I am a firm believer with related rates. Oops, got to zoom out. Now, I'm a firm believer with related rates that a picture is worth 1,000 words. So the problem tells me that I have an oil spill in calm seas. Ooh, oil bad. Now, at the center of my oil spill, I have a radius. And the area, and this is the key part of related rates, is that you have to figure out the formula that you're going to differentiate. Now, key thing here is it's asking about the change in area. It wants the change in area with respect to time. Actually, most of these relate problems are going to differentiate with respect to time. This kind of goes back to section 3.6 where we talked about that the derivative describes velocity. So our question is how fast is that changing? Now, the problem gives us some information. It tells me the derivative of radius with respect to time is 30 meters per hour. So what that tells me is every hour the radius gets 30 minutes, or 30 meters longer. So that's after 1 hour now. This is so not a circle, it's not even funny. And so now after an hour, this is plus 30 after an hour, and 30 again, and 30 again, and 30 again, and 30 again, and things are getting bigger, bigger, bigger. It also tells me that my critical time that I am worried about is when the radius is 100 meters. So let's look at what we have to do. Now, that geometry teacher of yours, I'm sure, pounded this into your head. The area equals pi times the radius squared. And being a good boy from the South, when I came home, my father told me, pi aren't square, you fool, pi are round. And there's your terrible math joke of the day. Now, for me to find this, I need to take the derivative with respect to time of both sides. So I'm going to say d dt of a equals d dt of pi r squared. Okay. Now, derivative of this is just dA dt. Oh, look, now I've got what I'm looking for, and I've just got to solve this equation. And then I'm going to go, okay, well, so that's pi times the derivative with respect to time of r squared. And I can pull that pi out because it's a constant, 3.14, 159, 26535, 8979, etc. Now, chain rule this, I've got to say, all right, I'm going to do the derivative with respect to r, so that's pi times 2r, because I'm going to come over here and we say, well, r is a function of t, and then that means that derivative of r with respect to t is that. And so, and then I've got times dr dt. Wait, wait, what did they tell us? They told me the derivative of radius with respect to time is 30. They told me the radius is 100. And look, all I have to do here is substitute in, and I'm going to be able to solve for dA dt. So dA dt equals pi times 2 times 100 meters times got lost there, meters per hour. Okay, well, multiply all that together. 2 times 100 is 200 times 30, 6,000. 200. Yep, 6,000 meters squared. Notice this is area, so I should have meters squared per time. Oh, not 6,000 pi. My apologies. So every hour, an additional 6,000 pi. So if we believe that pi is 3, that's 18,000 square meters per hour. It's actually a little bit more than that. It's probably closer to 20. 20,000 square meters, that's a lot. So spilling oil is bad, but this is good math that helps me model what's going on. There's going to be several of these videos. Just keep checking in. The key thing is finding this variable and being able to pull how are things changing and how are things at static points. Hope you found the video useful, and good luck as our semester continues.